OK. So consider this section kind of a bonus topic if you're really curious about how DNSSEC works at its very lowest level. This is the point where I think things start to get actually kind of confusing because of how deep into the protocol we're getting. So we're not going to test you on this, but in case you're curious and you want to see more of the design, I'll show you the very final piece so that I can do the full DNSSEC walkthrough. But if you don't like this, you're totally welcome to just stop here. If this walkthrough, the second attempt, made sense to you, that's great. You can stop here. This, I think, gives you all of the intuitive and implementation details that you need for this class. But for the very curious, let's quickly go through the final piece of the puzzle. So this is actually not a slide that I've ever checked for correctness. Maybe someday we will do that. And if I do, I guess we'll have to re-record this. Oops. But this is my guess, at least, for why this exists. So the reason, at least my guessed reason for why we want to do this, is because sometimes servers want to change their keys. So for example, if an attacker compromises a private key, like it gets stolen, then the name server might want to switch to a different key pair. So in order to do that, the name server would have to inform its parent that the key has changed. So remember that the parent has to sign the public key of the child. Therefore, if the child changes its keys, they have to tell the parent, and they have to say, well, hey, mom, I got hacked, and I have to change my keys. Can you sign this new key that I've generated? And then the parent gets all angry, and it's just kind of a mess. So we don't really want to have to go back and forth and change certificates every single time between two different servers, because that's kind of annoying. So the solution, and it's kind of weird, is to actually split every name server into two. So each name server has an upper half and a lower half. So now, if you think about the lower half's key getting compromised, they would have to report to their parent. But if we split every name server into two name servers, who is the lower half's parent? It's the upper half. So in other words, your parent is yourself. You're the same name server. So if the lower half's public key or private key gets compromised, they still have to report to their parent. But instead of talking to another name server that's complicated, you can just talk to yourself and say, hey, me, I've broken my key and I have to change it. And myself, I would answer by saying, yeah, that's fine, rock on. I'll give you a new public key and a new certificate, and everything is good. If that sounded weird, it's probably because it is weird, but that's at least my guess for why you might want to do something like this. Maybe it's totally wrong. Who knows? OK. Blue slides, out of scope. Anyway, this is what the design actually looks like. So we'll split every name server into two, possibly because of key compromise, maybe because of something else. But this design for sure is correct, or what actually happens. So each name server now has an upper half and a lower half. In other words, every name server is pretending to be two name servers in disguise, even though it's actually the same machine doing all of the work. So now each name server has two key pairs, one for the upper half and one for the lower half, and they get names. The upper half is called key signing key, and the lower half is called zone signing key. And because each name server now acts as two, what's going to happen is the upper half will endorse the lower half using the same strategy we've used of signing public keys. And then the lower half will endorse the upper half of the next name server. And then that upper half will endorse its lower half. And then that lower half will endorse the next name server's upper half. So we've basically taken the same chain we've already seen and just made it twice as long. And these are the names we give to the upper half and the lower half of each name server. That's why everyone has two key pairs. So here's at least one example. The berkeley.edu name server now has an upper half and a lower half. The upper half keys are called key signing keys. The lower half keys are called zone signing keys. So what you'll do is you'll have your upper half endorse your lower half. And the way you do that is you use the upper half's private key, that's the key signing key, to endorse the lower half's zone signing key. That's the lower half's public key. So it sounds complicated, but it is just a certificate that says, if you trust the upper half, I'm going to sign the lower half's public key. Now you trust them too. And then the lower half could delegate trust to someone else, or they could just sign the final answer if needed. So the resulting structure is basically the same certificate chain, but everyone signs twice instead of once. So in the original path, it would just be something like the root name server endorses the .org name server, which endorses the CS161.org name server, and then they sign some records. That's the original root of trust. The new root of trust is just twice as long. So this one arrow becomes two separate arrows, this arrow becomes two separate arrows, and this arrow becomes two separate arrows as well. So we're basically just doubling the length of the certificate chain, but it's still all certificates. The upper half of the root endorses the lower half of the root by signing that public key. The lower half of the root endorses the upper half of .org. The upper half of .org endorses the lower half of .org. The lower half of .org endorses CS161.org's upper half. That upper half endorses the lower half. That lower half endorses the answer. So it's the same chain as always, just twice as long. And at the risk of getting even more complicated, one key signing key could technically sign two zones, although it's not shown further here. OK, so that's the chain now twice as long. Great. This is the note that we talked about earlier. You don't have to authenticate NS records because they're not needed for verifying the final answer.